Hi, dear listeners. Now I am explaining how to achieve total internal reflection and how a light carry a lot of information through the optical fiber. To achieve total internal reflection, we need to know the basic optical laws. A fundamental optical parameter of a material is the refractive index or index of refraction. The refractive index of a material is defined as the ratio of speed of light in free space to the speed of light in a material. Therefore, the refractive index of a material N is equal to C by V, where C is equal to speed of light in free space, V is equal to speed of light in a material. Please look at the diagram for basic optical laws. You look at figures 1 and 2. When a light ray strikes a boundary separating two different media, part of the light ray is reflected back into the first medium and the remainder is refracted or bent and entered into the second medium. Because of the bending or refraction of the light ray at the interface, the speed of light in different material may differ that have two different refractive indices. The relationship at the interface is known as Snell's law and is given by N1 sin pi 1 is equal to N2 sin pi 2, where pi 1 is equal to angle of incidence and pi 2 is equal to angle of refraction. As the angle of incidence pi 1 in an optically denser material becomes larger, the refracted angle pi 2 approaches pi by 2 or 90 degrees. Beyond this point, no refraction is possible and therefore the incident ray reflected back to the first medium, that is totally internally reflected. If the angle of incidence pi 1 is increased, the refracted ray in the air is parallel to the glass surface as shown in the figure 2. This point is known as the critical angle of incidence. When the angle of incidence pi 1 is greater than the critical angle, the total internal reflection is satisfied. Thus, the light is totally reflected back into the glass. So here, the Snell's law is very important to satisfy total internal reflection. You look at the equation, the law of refraction or Snell's law is given by N1 sin pi 1 is equal to N2 sin pi 2, or N1 cos theta 1 is equal to N2 cos theta 2, where pi 1 is equal to angle of incidence, pi 2 is equal to angle of refraction, N1 is equal to refractive index of first medium, N2 is equal to refractive index of second medium. If pi 2 is equal to 90 degrees, sin 90 degrees is equal to 1. Therefore, the above equation N1 sin pi 1 is equal to N2. Beyond this point, that is pi 1 becomes critical angle, that is pi 1 is equal to pi c. Therefore, 1 sin pi c is equal to N2. And finally, sin pi c is equal to N2 by N1. And therefore, if you follow this equation, total internal reflection is satisfied. And then the light is propagated through the fiber core by means of internal multiple reflections. Now we need to discuss how a light can carry a lot of information through the optical fiber. You please look at the diagram or figure 3. The propagation of electromagnetic waves in the form of light through the optical fiber core. Internal reflections takes place in the fiber core. Now let us see how light can carry a lot of information through the fiber. In the electrical system, the data rate usually transferred over the communication channel by superimposing the information onto a carrier frequency, which is also known as electromagnetic waves. At the receiver or at the destination, the original information is extracted from the carrier wave Since the amount of information that can be transferred is directly related to the carrier frequency range, the bandwidth also increases. If the carrier frequency increases, the bandwidth also increases. Thus, larger information capacity is possible. In the case of fiber optics, optical fiber operates at optical frequencies, that is 10 to the power of 14 hertz, that operate in the 800 to 1600 nanometer wavelength band. Since the optical frequency is very high and the bandwidth is also high, thus provides a larger information capacity. So therefore, light can carry lot of information through the optical fiber because the light frequency is very high, say 10 to the power of 14 hertz, which is also called as a carrier frequency. Thank you.